Hi everybody, and welcome to the final video for chapter 12. In this video we cover section 12.4, which is about a fractally shape called the Mandelbrot set. So in this chapter we've explored three different fractal kinds of shapes. We looked at the Koch snowflake, we looked at the Sierpinski gasket, and then we looked at the twisted Sierpinski gasket. So what these three shapes have in common is that basically you can zoom in or zoom out on them as much as you want, and you'll see essentially the same thing. So with the Koch snowflake and the Sierpinski gasket, the more you zoom in is totally irrelevant. You will see the same thing at every level of magnification. With the twisted Sierpinski gasket, the more you zoom in, you may or may not see exactly the same figure you started with, but you'll see an approximation of what you started with. The Mandelbrot set is kind of like that. If you zoom in or zoom out on it, you will see copies of itself. And so that's one of the things that, it's one of the features of, for example, the Sierpinski gasket, is that it contains copies of itself. As you zoom in, you see the exact same picture, which means that the Sierpinski gasket is sitting inside of itself. The Mandelbrot set has that same feature. There are infinitely many copies of the Mandelbrot set inside of itself. However, its self-similarity is extremely approximate. So as you zoom in, you will see copies of itself in there, but depending on where you decide to zoom, you'll see all sorts of wacky other stuff too. So it's sort of fractally in the sense that it's sitting inside of itself. It is approximately self-similar, but it's not exactly self-similar like the Koch snowflake or the non-twisted Sierpinski gasket was. The Mandelbrot set was one of the first fractally shapes discovered, and it's one of the most beautiful and trippiest objects in mathematics, and that's why we're concluding chapter 12 with it. It's just a crazy object, and people didn't quite understand how crazy it was until technology advanced to where we could visualize it appropriately, but I'll show you some videos of it, of zooming in on it, and it's pretty crazy. So as I said, in this section we will introduce one of the most interesting and beautiful geometric fractals ever created. It's an object called the Mandelbrot set. It's named after the mathematician Mandelbrot. Some of the mathematics behind the set goes beyond this book. Okay, it's just beyond the scope of a single section of this course. So I will show you where the set comes from, but I'm going to skip a lot of the messy math details. I'm just going to give you the big idea of where the set comes from, because if we wanted to do all of the math, it would take, I don't know, probably 3 or 4 class periods or something. And it's not worth dedicating that amount of time in this course to this object. Okay, so we're going to start by doing a brief visual tour. This is what it looks like globally. If you're zoomed out sort of all the way, it's kind of just a black blob, and it has little like sub-blobs attached to it. And so some people have described these blobs as fleas. So the Mandelbrot set looks like a flea whose body is made up of this heart shape here. His head is right here. His antenna is here. But of course, you'll notice there are smaller fleas sort of attached to the bigger flea. And we can only begin to understand the full extent of all these sub-fleas when we look at the finely detailed close-up of the boundary of the Mandelbrot set. So we're going to start by zooming in right here. So this next slide shows zooming in there. So there's sort of a zipper-looking shape. So you can see all these little like black blobs that are attached to the bigger blob. If you zoom in more, the secondary fleas have fleas themselves. So the sort of like black blobs attached to black blobs keeps going forever. There is tremendous amount of variation though in the regions surrounding the individual fleas. So the images we see here are pretty trippy. It's like what a trippy coral reef would look like. You have sort of urchins and seahorse tails here. Like there's a seahorse tail there wrapped around. There's another one right there. When we magnify the view around the boundary even further, we see a virtual sea of anemone and starfish. So you have to use your imagination, of course, but there's like a starfishy kind of thing. And actually, if you squint hard enough, I think that right there is a copy of the Mandelbrot set itself. So if you zoom in like 1,000,000 times, you can start seeing copies of the original set. And there are actually infinitely many copies of this set inside of itself. So here's another trippy image. This is a zoomed in image of the seahorse tail. and a further close-up brings you something like this. I mean, it's just kind of like, it looks like a Jimi Hendrix album cover, right? Like it looks like something that would be on pot-inspired rock from the 70s. And zooming in further, what do you know? There's the Mandelbrot set again. So it appears inside of itself, and this version of it is just surrounded by these swirls of these seahorse tails and spirals. Okay, before we move on to the math here, let me just show you a video. So this video takes the set and starts zooming in on it. It goes kind of fast. So here we zoom in on the zipper here. And actually that right there might be a copy of the Mandelbrot set. I'm not sure because we're not going to zoom in on it. This video is 10 minutes long. We will not watch the entire thing. So here we're at like 200 times magnification or something, zooming in on these little spirally things. There's some seahorse tails sticking off of that. There's a little nebula looking thing, right, like a galaxy looking thing. So all of the black here is part of the Mandelbrot set. So this is, all these wacky little spirals are part of the set. And this video chooses to zoom in on a different section than what the slides do. So we might not get to the Mandelbrot set again in this video, or at least the section we're going to watch. Here's like a double galaxy thing in here. So let's keep your, so these nested things here might be Mandelbrot sets, just versions of the original picture. And so now we're at probably, 2,000 times magnification or something. So we've really zoomed in. You can ignore that email. Okay, so if you keep watching this video, you will eventually go to like 20 million times magnification, and it just keeps having this wackiness like this, right? It's just kind of a really, it's trippy, right? So you can imagine, and I imagine the mathematicians did do this, right? You can imagine kicking back under the influence of something and just staring at this for hours, right? And there you go. There's a little double galaxy thing like we've seen already. So here's a copy of what we've seen already, and this copy occurs at like 2,000 times the magnification of what we saw originally. And I'm wondering if we ever get to see the original flea picture again. Yeah, it looks like it's not going to do that for me. But anyway, so it's just a crazy object. All this black is part of the object, right? So you're getting all sorts of crazy spiraling and seahorse tailing, if that's a verb, and so on. So, if you want to actually watch all 10 minutes of this, you can see the title here. But again, it's just a crazy shape. You just zoom in forever and you keep seeing this wackiness. Okay. I hate that PowerPoint does that. Where was I? Okay. So anywhere we choose to look at these pictures, we will find, if we magnify enough, so if you magnify 1 billion times or whatever, you're going to find copies of the original Mandelbrot set, and it's always surrounded by an infinitely changing, but always stunning background. The infinite approximate self-similarity of the Mandelbrot set manages to blend infinite repetition, but also infinite variety, creating a landscape as consistently exotic and diverse as nature itself. So what this is saying is that no matter where you choose to zoom in on the set, you're going to start seeing the original set again. You're going to see the original picture again. But what it's surrounded by could be totally different depending on where you decide to zoom. So back in this original picture, if instead of zooming in this zipper part, I decided to zoom like right there, and then, just kept sort of like jumping around in here zooming, it's possible that the next time I see the Mandelbrot set, it's not surrounded by tails in this configuration. It's surrounded by those double galaxies we saw, whatever. So again, it's just a crazy figure. So now let's deal with some math of this figure. Again, the math here, the math that we really need to build this set goes beyond the scope of the course. So I'm just going to give you some big broad strokes here, some broad outlines, and just give you the big idea, right? You're not going to be dealing with these manipulations yourself. So how does this come about? It comes about through a recursive process. So that should not be surprising because the previous figures we have looked at came about this way also. The Koch snowflake and the Sierpinski gaskets came about by recursively using the same process over and over again. So you take a triangle, cut a hole. Take those triangles, cut a hole, right? And you do that indefinitely. The same kind of thing happens with the Mandelbrot set. The computations here, though, involve complex numbers. And so I don't know how familiar you are with those. It's possible the last time you saw these was 5 years ago in a high school algebra course. And that's okay. So I'm just going to walk you through the little bit we need to know about them now. The basic building block for complex numbers is the number I equals square root of -1. Now, you may very well feel like when somebody writes this down, square root of -1, your reaction might be square root of -1 does not exist. And my reaction to you would be, I mean, sure, it doesn't exist, but pretend like it does. And when you pretend like it does, give it the name I. And off we go, you know? So people like the Greeks would just be shocked by an expression like this, square root of -1. They would say, what are you doing? This is nonsense. But it turns out that if you just give the square root of -1 a name, if you call it I, and just go with it, it creates a very interesting class of numbers called the complex numbers. Any complex number can be written as the sum of a real number plus a real number times I. So complex numbers come in two pieces. You have a piece that's not attached to the I, and then a piece that is attached to the I. And either of these pieces can be 0 if you want them to be. It doesn't matter. Now, what matters for us is that every complex number can be plotted inside of a coordinate system. So -2 plus 3i, you can just plot that at -2, 3. 3 plus 2i, you can plot that at 3, 2, if you want to. -1.5 I can be plotted at -1, -i down here. So this -1, you can think of it as a -1i. This +2, you can think of it as a +2i. And this +2 is just a literal +2, like the real number 2. So to understand where the Mandelbrot set comes from, you need to understand this idea, that every complex number, if you want to, can just be plotted inside of a coordinate plane like this at the point AB. So A plus BI gets dotted down, at the point AB. So -2 plus 3i gets plotted at the point -2, 3. So complex numbers have a geometric interpretation. That's all this is saying. If you want to start plotting these numbers, you can plot them if you want to. You plot them in this coordinate plane here. Now, the key concept in the construction of the Mandelbrot set is that of a Mandelbrot sequence. A Mandelbrot sequence is an infinite sequence of complex numbers that starts with an arbitrary number that we call the seed. Now, remember that the snowflake and the Sierpinski gasket also started with a seed. It's just that for those figures, we started with a triangle, and we either added to it or took holes out of it, right? We punched holes in it in the case of the gasket, and we added to it in the case of the snowflake. In this case, to build the Mandelbrot set, we're not starting with a triangle as our seed. We are starting with a complex number instead. But the idea is still the same. From the seed, you get a new number. From that number, you get a new number, and so on. Just like with the Sierpinski gasket, we started with a triangle, and from that we got a triangle with some holes in it, or a hole in it, and from that we got a triangle with some more holes in it, and from that we got a triangle with more holes in it, and so on. It's the same idea here. We start with our complex number seed. From that seed we get a new complex number. From that complex number we get a new one, and so on. We do this infinitely. The way that we go from seed to the next number is we square the seed and add the seed to itself. So seed squared plus seed, that gives us a new number. We call that S1. To go to the next step, we square S1 and add the seed to that. Then we give that a name. We square that, add the seed to it, give that a name, and so on. So at every step in this process, you're adding the seed. So, right, plus S, plus S, plus S. And what are you adding the seed to? You're adding it to the number you got in the previous step, squared. So just like right here, right? S1 was the number we got in step 1. So in step 2, we square it and add the seed to it. And once we've done that, we give that number a name, S2. Then we square that, add the seed to it to get a new number, and so on. We do this forever. So here's a description of what we're going to do. Choose an arbitrary complex number s. We will call s the seed of the sequence. Set the seed to be the initial term of the sequence. So the seed is where we start. To find the next term in the sequence, what you do is you square the preceding term and add the seed to it, just like we did on the previous slide. That's all this is saying. If you want to find the next term, square the previous term and add the seed to it. So just like here, if you want to find S3, find the number in step 3, what did you do? You took the number you found in step 2, squared it, and added the seed to it. Each point in the Cartesian plane is a complex number and thus the seed of some sequence. So back in this picture here, no matter where you decide to plop a dot down in this plane, like plop a dot right there, that number represents a complex number, and you can take that number as the seed of a sequence if you want to, as the start point of a sequence. That's all that's saying. The pattern of growth of that Mandelbrot sequence determines whether the seed is inside the Mandelbrot set or outside. So in the Mandelbrot set itself, everything black was a point inside the set, and everything not black was outside. So in the case of non-black points, the color assigned to the point is also determined by the pattern of growth of the corresponding Mandelbrot sequence. So we're going to delve into a little bit of detail here because this doesn't really make any sense without examples or anything, but here, basically what that slide is saying is, when you build a Mandelbrot sequence, you are simply building a list of numbers, S, S1, S2, S3, and so on. The growth of that sequence determines what's black and what's not black inside of the picture. That's what that slide is saying. Now, how does that work? Well, we're going to explore that, but that's what this is saying. The pattern of growth in that sequence determines whether the seed is inside the Mandelbrot set or outside. So in other words, for a given seed, we're going to see how its Mandelbrot sequence grows. If it grows a certain way, we're going to color the seed black. If it grows another way, we're going to color the seed not black. Okay, so here's an example of a Mandelbrot sequence. So if you start with s equals 1, well, the next step says take the previous term, square it, and add the seed to it. So we get 1 squared plus 1 is 2. In the next step, we take this previous number, square it, add the seed to it, and we get 5. In the next step, we take the previous number, which was 5, square it, add 1 to it, and we get 26, etc. This goes on forever, right? In this case, these numbers will just keep getting bigger and bigger, right? 677 squared is really big, and then plus 1. And then 677 squared plus 1 all squared is even bigger, and so on. So these numbers here are becoming arbitrarily large. The pattern of growth of this Mandelbrot sequence is clear. It's what we just said. The terms are getting larger and larger, and they do so pretty fast, actually. Geometrically, this means that the points in the Cartesian plane that represent the numbers in the sequence are getting farther and farther away from the origin. Now, why is that? Let's go back to the picture. The origin here, right here where the axes meet, that corresponds to the number 0. So the number 1 is right there. The number 5 is over here. The number, whatever the next number in the sequence was, 26, is even farther off, it's off the screen. And then 677 is even farther off the screen. They just keep moving to the right. So numbers that get bigger and bigger and bigger are shooting away from the origin. So up here is like a billion I. Over here is like negative a billion. And down here is like negative a billion I. Okay. So for this reason, we call the sequence escaping. It escapes from the origin. It just keeps moving farther and farther away. In general, when the points that represent the terms of a Mandelbrot sequence move farther and farther away from the origin, we call it escaping. So that's a technical term. The basic rule that defines the Mandelbrot set is this. Seeds of escaping sequences are not in the Mandelbrot set and must be assigned some color other than black. Okay, this is the key idea. Suppose you have some number, like, I don't know, a half, right, whatever. You want to know, do I color that number black and include it in the set, or do I color it not black, thereby not including it in the set? To answer that question, you have to construct its Mandelbrot sequence and ask, is it escaping? Does this sequence go away from the origin or not? So in this case, we started by considering the number 1. The number 1, its Mandelbrot sequence escaped from the origin. It moved away. In this case, it moved infinitely to the right. But as long as you're moving away some way, like maybe it could shoot up or shoot down or shoot diagonally down, whatever, as long as you're moving away from the origin, you do not get colored black. You get colored some other color. So again, this is the key idea, so let me just repeat it. You want to know if a given point inside of that plane is in the Mandelbrot set or not. What you do is you take that point and construct its Mandelbrot sequence just like we did right here with 1. If that sequence is escaping, then you don't color that sequence black, or you don't color that original seed number black. But if that sequence did not escape, then you would color it black. Okay, so while there's no specific rule that tells us what color should be assigned, it just says here some color other than black, right? That's pretty vague. The overall color palette is based on how fast the sequence is escaping. So the sequence that we already investigated that starts with 1, that escapes pretty fast. It goes from 1 to 5 to 26 to 677, then to some number in the thousands, etc. If you started with 1,000 instead, so imagine starting right here with 1,000. Your very next number would be 1,000 squared plus 1,000. That's huge. Then you take that huge number, square it, add 1,000 to it. That leaves even faster than 1 does. Those numbers become huge faster than this sequence does. So in other words, some numbers escape faster than others. So the typical approach is to use hot colors such as reds, yellows, and oranges for seeds that escape slowly, and cool colors such as blues and purples for seeds that escape quickly. So you can just sort of measure how fast a seed is leaving the origin and color it accordingly. That's why there are colors in the like that video we looked at. So the seed for S equals 1 example escapes very quickly. So we would color the point blue. Because blue means quickly in this context here. Think about -1 on the other hand. So if you start with -1, -1 squared, what is that? That's -1 times -1, which is +1. Well, 1 plus -1 is 0. So when you start with the seed, your very next step is to square it and add the seed. And when you do that, you get 0. Now in the next step, you take 0 and you square it, you add the seed. Well, 0 squared is 0, plus -1 is -1, and oh, you're back to the original number. So you went from -1 to 0, and then from 0 back to -1. Well, we know where -1 goes, right? We square -1, add -1, and we get 0. So if instead of starting with 1, you started with -1, this sequence just goes -1, 0, -1, 0, -1, 0. -1, 0. It will just keep doing that over and over again. So in this case, the pattern, these numbers do not leave the origin. They don't escape, right? They don't just grow indefinitely. These numbers just sort of bounce around back and forth. They stay bounded. And so in this case, you call it periodic. So basically, like, if the sequence starts repeating itself, and this one did, -1 to 0, -1 to 0, started repeating, you call it periodic. When the Mandelbrot sequence is periodic, the seed is a point of the Mandelbrot set, and you color it black. The reason the seed is a point of the Mandelbrot set is because the seed does not escape the origin. Anything that doesn't escape, anything that does not just grow indefinitely, is by definition part of the Mandelbrot set. Okay, now here's another example with -0.75, and I'll just say you can verify all this using a calculator. If you square -0.75, then take off -0.75, you get -0.1875, and if you iterate that, you get -0.714844, and so on. So these numbers here also don't escape the origin. They don't repeat themselves either, but that's okay. All that matters is that they don't escape the origin. Therefore, yeah, it says here you can't really tell, but you can always ask a computer to show you the first billion terms or whatever, as you go farther and farther out, the sequence of the terms will get closer and closer to negative 0.5. So again, these numbers do not grow away from the origin, and therefore this number gets colored black. So here is another example. This one involves an actual complex number now. If we start with I, well, the next step is to square I and then add I. Well, I is the square root of negative 1. So when you square it, you get negative 1. So the next step gives you negative 1 plus I. Now when you move on, you have to take negative 1 plus I and square it, and then add the seed to it. And I will just tell you, but you can verify this on your own, that if you square negative 1 plus I, you will get, let's see, what is it? Negative 2I. So you have negative 2I plus I gives you a negative I. Okay, so you start with I, you go to negative 1 plus I, then you go to negative I, and now if you square negative I, that's negative I times negative I, the negatives cancel out, and then I squared is negative 1, so you're back at negative 1 plus I. And we know where that goes to negative I. So if you start with I as your seed, then you end up in this pattern that repeats itself. So you color that point corresponding to I black, because its Mandelbrot sequence does not escape. It does not grow indefinitely. Okay, so if you start with this seed, here's what that does. Again, you can verify this on a calculator or whatever, but this is what happens. With this seed here, you also don't grow to infinity. Right? These numbers are sort of stable. So these numbers also, this original seed is also part of the Mandelbrot set. Okay, so the Mandelbrot set is simply all of these different seeds whose Mandelbrot sequence don't go to infinity. And if you color all those black, you will get the set. And that's basically the idea here. So it's kind of wacky, but again, let's go back to the original set. How does this drawing know that points in here are black and points out here aren't black? What a computer or whatever will do is they'll take a point in here, square it, add the seed, right? They'll take each number, a particular number here, treat it as a seed. They will square that number, add the seed. Take the result, square it, add the seed. Take the result, square it, add the seed, and so on. The computer will construct a list of numbers. If that list of numbers is not just growing indefinitely, then the original point is black. So what does that mean? That means that this point right here, if I construct its Mandelbrot sequence, I don't really know what it does exactly. All I know is that the sequence does not escape. It doesn't shoot off to infinity. But a number out here, like a number right here, that guy's sequence does go to infinity, and that's why he's not colored black. So that's how you build the Mandelbrot sequence. It's a Mandelbrot set. It's a recursive process, just like the snowflake and the gaskets. It is more complicated because it involves this iteration of numbers, of complex numbers. But the idea is essentially the same. You know, it's more complicated. So as this last slide says here, it says there are a few technical details that we omitted. That's kind of an understatement. There are tons of details we omitted, but the key ideas of what we discussed, of like constructing a Mandelbrot set and just measuring whether it goes to infinity or not, that's the key idea behind building the set. The Mandelbrot set provides a bounty of aesthetic returns for a relatively small mathematical investment, because really, you know, all you're doing is multiplying and adding, right? I mean, that's every step in the sequence. Squaring is just multiplication, then you add the same number you started with, right? So on some level, this set is achieved simply from multiplication and addition. So that's what it means by a small mathematical investment. But it's just a bizarre thing. You know, it's just, you wouldn't think that by just doing addition and multiplication in this way that you could get a shape so complicated. But you do. Okay, so when it says here it's one of the most popular mathematical playthings of our time, it's not just that. Okay, there are other reasons to study it, but one of the reasons people like it is because Mathematicians love when you can take something simple and get something really complicated and bizarre and beautiful out of it. And so again, this set arises simply from repeated multiplication and addition. Okay, that's not a complicated process, right? I mean, everybody knows how to multiply, everybody knows how to add. But from those two really simple processes, you get this crazy picture. You wouldn't expect that, and yet there it is. Okay, so with these fractals under our belt now, after having studied these, we are done with Chapter 12.